Now suppose you're given a whole bunch of points and want to know if they actually satisfy a linear function. How can we proceed? Well, let's take a look at an example and see exactly how we'd move forward. So here's a set of ordered pairs, a set of points in the plane. And I want to know if they actually satisfy a linear function. Well, one thing I can do is just make a little chart of those values. And then it turns out that if we see that the change in x being constant implies that the changes in y's are constant, then in fact we have a linear function. Let me show you what I mean. So let's just first of all fill in this table with these points. So 2, 4, 4, 3, 6, 2, 8, 1, and finally 10, 0. Now what I'd like to do now is, so those points are now depicted here, and what I'd like to do is take those points, and I want to take a look at the changes. Because really, a linear function is all about how the function is changing. So let's take a look at the change between here and here. What that means is that I want to look at the difference. I want to take 4 and then subtract 2. That change, you notice, is 2. So it's going to be 4 minus 2. That's just the change. Let's take a look at this change right here. That's 6 minus 4, which is 2. Let's take a look at this change right here. That's 8 minus 6, which is 2. And let's take a look at this last change, 10 minus 8, which is 2. So notice we have the constant change here. This change is constant throughout. Now, if that implies that the changes in y's are constant, then we know that, in fact, this satisfies a linear function. So let's see what the changes in y's are. So here I take 3 and subtract 4. And I see negative 1. Here I see 2 minus 3, and I see negative 1. Here I see 1 minus 2. I see negative 1. And here I see 0 minus 1. I see negative 1. Well, notice that these are all the same. So constant changes in x imply constant changes in y. That means that, in fact, this data does, in fact, conform to a linear function. Neat. So that's a sort of a one way of testing and seeing if we have something that's conforming to a linear function. If we have constant changes in x, that implies constant changes in y's. That means that we are in Fat City, as they say. So let's take a look at another example. Here's a bunch of points. I want to see if they conform to a line, linear function or not. So I immediately make a chart. So I just converted these things to the chart, you see. Okay, and now let's take a look at the changes. If we have constant changes in x, and that implies constant changes in y, then we're in good shape. So let's take a look. So I'll take negative 3 minus negative 6. So we add the opposites, so that's going to be 6 minus 3, which equals 3. What about here? 0 minus negative 3 is 3. 3 minus 0 is 3. 6 minus 3 is 3. We have constant changes in x. That's a good first step. If they imply constant changes in y, we know that, in fact, this satisfies a linear function. Let's see what happens. So here I take 10 minus 12. That equals negative 2. Here I see 8 minus 10. That's negative 2. This is looking good. 4 minus 8. 4 minus 8 is negative 4. Ouch. I can stop right here because I see, in fact, these aren't constant. Let me do one last one, though. Negative 2 minus 4 is negative 6. No way. These are not all the same number. There is not a constant change in y to correspond with the constant change in x. So this is, in fact, not going to conform to a linear function. Sorry, but at least we see that we can do it. When we have constant changes in x and they imply constant changes in y, then we know we've got a linear function.